So shown here, there's an engineer who's working at an instrument, and at his disposal, he has 8 different controls. He can adjust the pressure, the temperature, the humidity, the flow rate, the RF power, the bias, the current, rotation, and time. So this particular case is someone who's processing a semiconductor wafer. There's a lot of different variables that they have at their disposal, and understanding how to find an optimal solution for a process or to be able to understand the effects of a variable with an efficient experiment is the goal of today's talk. So the outline, I'll first define a lot of terms. So unfortunately, I have to define for about 8 or 10 slides worth of material, just so that we have a common vocabulary and a common language to talk about our experimental design. But I'll do it in terms of an experiment. So I'll talk about a specific hair growth experiment, and you'll be able to understand the terminology. And then we'll go into screening design. So the first thing I'll talk about is comparative designs, where we just want to see what effect a single variable has. The second type of experiment we'll talk about are screening designs, where the goal is to understand which variable, like in this guy's case, which of these 8 variables are most important. And so being able to understand the sensitive variables is the goal. There'll be an activity, so there'll be a hands-on activity where the audience gets to participate in. And then, time permitting, I'll talk about the full and fractional factorial experiments before concluding. So my first set of definitions, we want to distinguish between an observation and an experiment. And a lot of the public often mixes these up. And a lot of news reporters, hopefully there's not a lot of news reporters in the audience, they tend to mix these 2 terms up. So let's first talk about an observation. In an observation, the goal is to observe and measure variables without trying to influence the response. So you have no control over the system. You're just watching what happens as something progresses. In an experiment, which is the main difference, you deliberately impose some type of treatment in order to observe a response. So you're going to intentionally interact with the system so that you can cause a response. So if you design it correctly, an experiment can give evidence for causation. However, an observation cannot. Oops. Okay, so let's talk about the first experiment. So the first experiment is a hair growth experiment. So imagine that you work at a pharmaceutical company, and your boss and your team has just discovered this new Hair Grow TM. It's this new shampoo that helps grow more hair. So you're actively going to try to patent it, and so you've seen these results. So in month 1, there's no hair. Month 13, there's lots of hair. So your boss, though, is a little bit skeptical. He says, design an experiment to evaluate how valid this claim is. We can't go to our shareholders and promote this product until we know for sure that it's what's causing the hair growth. So you have to design an experiment to evaluate the claim. So some definitions. The first definition is the factor. The factor is the explanatory variable. It's also known as the independent variable. So it's X. It's what you're varying. It's the treatment. It's what you're going to vary in order to look for the response. So at your disposal, you can try the hair growth formula, or you can try plain shampoo. And what you want to compare is the response to this particular factor. So the factor is the explanatory variable, and then the factor can have different levels. The level is the specific value of this particular treatment. So you can have one level, which is 1 teaspoon of the hair growth formula, or you can have a different level, which is 4 teaspoons of the hair growth formula. So the different levels are the specific values of that treatment. Now, when you design an experiment, you want to choose a wide range. You want to choose a wide range so you can explore the full parameter space. But you also have to be careful that it's a safe range. Like, you don't want to have something that is too high of a concentration of something. And you also want to select a useful range. So you wouldn't tell your client, okay, you have to put 32 bottles of the shampoo in order to, or the formula in order to grow 1 hair. So you want to select a useful range, a wide range, and a safe range. Okay, so let's do, so I'm going to step aside from that hair growth formula experiment, and let's do a single variable experiment. So I have with me 3 tuning forks. So I have tuning forks of different lengths. So I have a long one, I have a medium-sized one, and I have a small one. And the experiment that I want to study is how does the length of the tuning fork affect the frequency that it produces? So this is a scientific question that we want to study. So we have 3 different forks. So we want to set up our design of experiment and use the terminology that I just defined. So length is the factor. It's what we're going to vary. So we're going to vary the length of it, and what we're going to measure is the frequency or the response. How does it sound? So we're going to figure out how does the frequency depend on the length. Okay? So I should ask the audience, which one do you think is going to produce the higher pitch? Okay, so we have some musicians in the audience. So the musicians in the audience say that the smaller one will produce the higher response. So let's validate that. Oops, let's validate that. So what we're going to do is we're going to plot the frequency response as a function of the length of the tuning fork. So our x variable, which is the explanatory variable, which is going to explain the response, is going to go on the horizontal axis. And the y, which is the independent variable, or it's also known as the response variable, this is going to be what we measure. So we're going to see how does it depend on the length. So I'm going to measure one length. So let's start off with the shortest one first. Oops. You got to hold it. Okay, everyone hear that one? Okay, now we play a slightly longer one. Was that higher or lower? Lower, okay. And now we play the longest one. Okay, so that's the lowest. So what we're doing is we varied the explanatory variable x, and we measured the response variable y. So we measure for a bunch of different lengths, and what we find is that as you make the tuning fork longer, the frequency that it plays gets lower. And we can graph this. So we measure a bunch of different lengths, and we graph it. So this is a single variable experiment. Question?
Frank, to your other experiment, what's a reasonable sample size that you need?
Okay, so the question is, going back to the previous experiment, what's a reasonable sample size you need for an accurate result? So I'll talk about sample size in a couple of slides, but that's a good question. You're anticipating, and it's good when the audience knows what's going to come next. So I'll talk about that in a couple of slides. Okay, so you can actually measure or fit this response to an inverse square law. So it actually turns out that the frequency is inversely proportional to the square of the length. So what we've been able to answer in our experiment is how does the length of the tuning fork affect the frequency. Okay, so now, as the gentleman from the audience pointed out, let's talk about sampling. So we first have to distinguish or differentiate between what's a census and what's a sample. So a census involves studying the entire population. So I don't know if people remember the 2010 census. People from the government came around every single neighborhood. They asked how many people live in your house, how many men, how many women, what age group, or what ages they are. It's very expensive and very time consuming. It's a massive amount of data, and it's great data, but you can't conduct a census every single time you want to answer a question. So what we do, so this picture here, it's supposed to represent 250 million people in the US, or 300 million people, the current population. So what we do is instead of studying the entire population, what we can do is we can study a sample of the population. So we study a part of the population in order to draw information or gain information about the whole population. And as the gentleman pointed out, if I make the sample size bigger, the better my inference about the way that the population will behave. So I need a large enough sample that I can make solid conclusions, but if I make too large of a sample, it's going to be very time and resource intensive. Now, there are different ways that I can do the sampling. So the first way is I can do a simple random sample. So what I can do is out of the original full population, I just randomly pick a certain number of people with equal selection probability. So I pick her, and I pick him, and I pick him, and I pick him, and I pick her. So I pick people at random out of the audience, and I ask you a question. So that would be a simple random sample. The larger I make it, the more accurate it is. The important thing with a simple random sample is the probability that I select you should be the same regardless of what your demographics are. Now, there's another type of sampling called stratified random sampling. In stratified random sampling, what I first want to do is to divide the population up into groups that are similar. so that I can draw conclusions about how a specific group behaves. So I divide each group into strata, and I do a simple random sample on each group. So for example, if I want to compare the differences on how men and women respond to my hair growth formula, I should first divide the population into men and women, and then within the men, I pick a certain number of people to be part of my experiment, or part of my measurements, and a certain number of women will be part of the trial. And so I do a simple random sample, so I randomly pick 10 men, I randomly pick 10 women to be able to do my study. Okay, so I do a simple random sample on each group, and I draw conclusions about the group. Okay, some more definitions. Experimental units. These are the individuals or things on which the experiment is done. So for example, the experimental units would be people. In the hair grow experiment, I'd have a bunch of different people as my experimental units. There's something called a placebo effect. The placebo effect, a lot of patients just respond knowing that they have a treatment, even if the treatment is not actually a real treatment, it's just a dummy pill. And so, for example, in this experiment, the placebo that we would give would be plain shampoo, so that we can compare whether our formula is actually doing something. We want to have a control group. A control group is the group that receives the placebo, so we can compare the effects of the treatment to a group that's received the placebo. Some more definitions. I think this is the last slide of definitions. Confounding variables. So there's always an infinite number of variables that can explain a particular event or a particular process. Some of them the scientist or engineer knows about, and these are the variables under their control. There are other variables that the researcher doesn't know about, and these are called lurking variables. They may explain the relationship between the explanatory variable and the response variable. And so there's a statement that says just because you have high correlation, meaning that the things are related, it doesn't imply that it's causation. So you don't always know that one thing causes another. So in this hair growth experiment, one of the possible lurking variables is the source of the hair loss. So for example, some people have androgenic alopecia, and some people have hereditary things that affect their hair loss. There could be another variable. There could be daily lifestyle. So diet is known to affect hair growth and also poor hair care. So these lurking variables, these are variables that the researcher in his experiment is unaware of when he's constructing the experiment. And so as a result of being unaware of these, there can be what's known as confounding, which is the effects of the response variable due to the explanatory variable and or the lurking variables. You can't tell what's causing it. It could be the lurking variables, it could be the explanatory variables that are causing the one thing to work or not to work. Okay, so I should pause. Any questions? I haven't answered the guy's question about how many experiments you need to do. I may have to answer that one offline. It's a more complicated question. Okay, any other questions? No? Okay, so yeah. Well, I say infinite in that you can always think of another variable that could possibly describe it. So when you think you've made a list, I can say, well, the temperature, well, the humidity, well, the day of the week, stuff like that. So you can just constantly add variables that may explain it, they may not actually explain it.
Like your tuning forks, we didn't ask about how dense the material they were made from.
Right, so we didn't talk about the density of the material, the width of the tuning fork, the separation, what material, whether we're in air versus in a liquid or something like that. Okay. Okay, so continuing on. So how do we get around this problem of confounding variables? How do we separate what we're interested in, which is the explanatory variables, from these noise factors, which are the confounding variables? There's something called a block design, and in a block design, you randomly assign treatments within each block of similar individuals, and you analyze each block separately. So for example, if gender plays a role, so this could be a possible confounding variable, first what we should do is we should separate the group into men and women, and then randomly assign some men our treatment, which is 1 teaspoon of our hair growth formula, or one teaspoon of our placebo, which is plain shampoo. And then we want to compare the results. We want to see, for men, does this hair growth formula produce a noticeable improvement? And then we're also going to study for women. We're going to see, does the hair growth formula produce a noticeable improvement? And we want to separate them initially because gender could be a variable that has an effect. And so we don't want to confound the effect of gender with the variable which we want to study, which is our formula. There's another way that we can get around the problem of confounding, and that's called match pair design. So in a match pair design, it's a common form of blocking where the subject receives 2 treatments in sequence in random order, or you get a pair of twins. You get people that are identical in every way except the treatment that you give them. So you have a pair, and so this could be a pair of twins, or you can have one person do it in twice, just in different orders. You randomly assign them whether they receive the hair growth formula or whether they receive the shampoo, and you compare the results. So for one pair of twins, you see it works. Another pair of twins, it's not very effective. Another pair of twins, it works. Another pair, it's not effective. And you compare all these different results, and you come up with a conclusion as to 50% of the time it helps. And so then that'll lead you to further studies. But at least you have a way to do comparison. The whole thing that I'm talking about at the beginning, it's very important that you compare. So one of the key things in a good experimental design is that there's a comparison being made. Okay. So this is the most important slide for today. I'm going to make sure that everyone understands it and that we go through it very carefully because this summarizes everything that I want you to learn from today. There are 3 key principles to good experimental design. If you follow these 3 key principles, then your experimental design will be good. The first is that you need to control the effects of lurking variables by comparing. So you're going to compare 2 or more different treatments. So you have to construct groups that are identical in every way except for the treatment. Then if you see there's a difference in the treatment, you've been able to get rid of all these other lurking variables because the groups are supposed to be identical in every single way. Now, you may not be able to construct the groups identical in every single way on your first try. So what you do is you randomize the assignment of the experimental units to the treatments to reduce the effect of lurking variables. If I just said, okay, I'm going to pick the people on this side of the room, which may be more men than this side of the room, and I give them one treatment and I give this other group the other treatment, I didn't do a good enough job of randomizing, and so I may be confounding the effects of lurking variables. So you randomize the assignment so that you can construct groups that are equal to each other or identical in every way except for the treatment. And then the last thing that you need to do is you need to replicate each treatment enough times to reduce the effects of chance variation. There's always going to be randomness, there's always going to be noise, and so if you do many different experiments, many trials, so going back to the question, how many trials do you need to do? If you do enough trials, then you're able to reduce this effect. And so if your data is what's known as normal, so Gaussian distributed, if you do averaging, so you make a lot of different measurements and you average the results, then you reduce the effect of the variation. And so the larger the sample size, the better the conclusions you can draw. So the three key principles: you have to control by comparison, you have to randomize, and you have to replicate. There's a quote attributed to George Box, a famous statistician, that says, "Block what you can, randomize what you can't." So in the blocking, you try to group them as much into identical groups as you can, but you can't create that many groups. You can't have thousands of groups. It'll be very hard to have enough people in each group. So you do randomization against the other variables so that you can get rid of the effects of confounding. So control, randomization, and replication are the 3 key principles. Any questions on this slide? It's very important that everyone understands this. Yes?
When you say replicate the third factor, is it just increase the sample size, or within the same sample size you can do some design of replication?
Okay, so the question is, for replication, do you mean increase the sample size, or within the sample that you have, just do more experiments? It could be both. Most of the time what you do is you increase the sample size, so you try more different people, because the sample that you, the people that you initially pick in your simple random sample, they may not be representative well enough of the population. So generally if you pick a bigger sample size, then you can reduce the effect that the sample that you originally picked was somehow biased in some way. So usually you pick a larger sample size. Now, if you're unable to pick a larger sample size, you can try doing more experiments with the sample size that you have. but it doesn't help you as much as if you pick different people. So picking different people would be better. Other questions? Yes?
Time is going to be interesting here because you could do the original one. Okay, you're doing pretty much at the same time. But if you're replicating, you're going to have to consider time in there.
Yeah, so time and what things change over time. So that's one of the reasons picking the same person multiple times is not a very good idea, because they have prior exposure and prior treatments. So ideally you want to have new people to be able to not have any prior exposure or prior effects. Other questions? Okay, so let's keep going. My advancer is no longer working. Okay, so let's study a bunch of different experimental designs, and we're going to evaluate whether these are good designs or bad designs. So we want to demonstrate cause and effect, and so we want to look at certain types of designs. TX means that a treatment is made during an interval. OBS means that an observation is made. And double dash means that nothing happens or a placebo occurs during that time slot. So what we're going to show is we're going to have like group 1 and group 2, and time progresses on the horizontal axis. So design A, so we randomly assign people to group 1 and to group 2. We give group 1 the treatment, we give group 2 the placebo, and then we observe the 2 results. And so is this a good experimental design? Well, we have to answer is, does it satisfy the 3 key principles? Yes, there's control by comparison, because we're going to compare groups 1 and 2. Yes, there's random assignment to people in groups 1 and group 2, so that's good. And replication. So when we say group, we're going to assume that there's enough people in the group that we have good replication. So this is a good experimental design, and what does it tell us? Well, if we see a difference between group 1 and group 2, we have evidence that the treatment causes the observed difference. Notice we don't have proof, and this is a key point that a lot of people forget. Just because you see a difference, you don't have proof, you just have evidence that there's a causal relationship. What about this design? We have one group, we give them a treatment, we make an observation. Is this a good experimental design? No. Do we have control by comparison? No. Do we have replication or random assignment? No. Do we have replication? Maybe. So this experiment, in quotes, can show evidence really of nothing, just that the observation happened after the treatment. Now, this type of experiment happens a lot. I don't know how many sports fans there are in the audience, but if you ever listen to ESPN and you hear stats like, Illinois football is 26-0 when they rush for 400 yards. That's this experiment. So the observation is they win. The treatment is they ran for 400 yards. So the people think, oh, all we have to do is run for 400 yards and we'll win all the games. So no, that's not a good experiment. That just shows one thing happens after the other. Parents are very famous for this experiment. Parents will say, I see you have a cold today. That's because you were standing outside in the rain yesterday. So that's the treatment is the kids standing outside in the rain. The observation is they have a cold, therefore standing outside in the rain causes colds. Parents do this all the time. Not a good experimental design. Okay, what about this design? We randomly assign people to group 1 and group 2. We make an observation before. We give a treatment to group 1. We do nothing for group 2. We make an observation after. Is this a good design? Yes. So we have control by comparison. We have random assignment, and we have replication. So this is a good experimental design. What do you think this design can show that the other one couldn't? What's the difference between these? The fact that I have an observation before. A before and after effect. We can see whether there's a change in response. So the key is, in the first case, we see that there's a difference in response. In this case, we can see a change in response. So now we can see, is there evidence that the treatment causes a change in the response? What about this design? We have 4 groups. We randomly assign people to 4 groups. Group 1 gets treatment 1 and then treatment 2 and then observe. Group 2 gets treatment 1 and placebo and observes. Group 3 gets nothing and treatment 2 and then observes. Group 4 gets placebo twice. So good experimental design? Yes. We have control by comparison. We have random assignment. We have replication. Now, this has two different treatments, treatment 1 and treatment 2. So what do you think this experimental design is, what's the goal of this experimental design?
Look at the interaction between them.
Okay, so look at the interaction between treatment 1 and treatment 2. So it can tell us several things if we compare the right groups. So if we compare group 3 and group 4, what can that tell us? If treatment 2 is useful by itself. If we compare group 2 and group 4, that tells us treatment 1 by itself is effective. If we compare group 1 and group 3, we can see whether treatment 1 and treatment 2 is better than treatment 2 alone. If we compare 1 and 2, we can see treatment 1 and treatment 2 is better than just treatment 1 alone. Compare group 1 and group 4, that's treatment 1 and 2 versus nothing. So there's actually 6 comparisons we can make, so 4 choose 2 comparisons that we can make. And so what this shows is that it can show evidence that treatment 1 or treatment 2 individually cause a response, as well as both taken together, whether they cause the same response or a different response. So this is what's known as a two-factor experiment. Okay, so now let's get into some screening designs. I think I have to pick up the pace a little bit, and then we'll talk about the LED activity. So we have a process, and this can be a system, this could be nature, it can be anything. And what we have is we have a bunch of inputs and we have some outputs. So the inputs are things that we can control. So we have these factors that are under our control, like temperature, humidity, pressure, and so forth. These are things that we can control. There's uncontrollable inputs. So temperature and humidity we can't control, let's say. But let's say that we can control like our spin rate or the pressure or something else. And then there's uncontrolled cofactors that can be discrete, such as different operators or different machines, and they're continuous ones like temperature and humidity. And we put all these inputs into the process, and the process spits out a bunch of different outputs. So this could be like we put in our hair growth formula, but then these inputs could be like different ages of people, and this could be different ethnicities or different genders, and then whether it works or whether it doesn't are our outputs. A screening design, so the comparative design, which is what I talked about initially, we're just trying to compare whether a treatment produces a response. In a screening design, the goal is to figure out which of the many factors are important. So both the inputs, which are the factors, and the outputs, which are the responses, we need to pick them carefully so that they match realistic conditions. And we usually assume that there's a linear relationship between the input and the output. So how do we accurately measure the slope for a linear relation? Because that's going to be what we're typically after. And the answer is we want to measure y for widely spaced x. And what we can see is, let's say that we want to measure the density of steel. So the density is the ratio of the mass per volume. So we have two different experiments. In this experiment, we measure two very closely spaced volumes, and we measure the two masses. In this case, we measure two widely spaced volumes, and we determine the mass. In which case are we going to get the more accurate slope? I kind of gave it away. It's in the second case. We can draw one line that can pass through those two data points. Whereas in the first case, there are a bunch of different lines and a bunch of different slopes that pass through those two data points. So if we want to measure the slope accurately, we should space our x variable as far apart as we can, but it has to be within a safe range of values. The next thing to look at is the multivariable screening experiment. So let's say that we have two variables, x1 and x2. So these are two possible things that can explain our response. And each one is going to have a low setting, which is -1, or a high setting, which is +1. So this is -1 for x1, and then +1 for x1. And then -1 for x2, and +1 for x2. So there are 4 points, and you'll notice that this particular design is identical to our design D, where we have two different treatments. And so, for example, if x1 and x2 are high, that could be something like we're giving this our hair growth formula, and we're also doing another treatment, which could be an improved diet, for example. So let's say our second factor is diet, and our first factor is our hair growth formula. So this point can represent hair growth formula plus good diet. This point could represent hair growth formula plus poor diet. This point could be good diet, but placebo shampoo. And this could be bad diet and placebo shampoo. So we have two factors, hair growth formula or shampoo, and we have good diet versus bad diet. And so we have 4 possible combinations, and we represent it graphically in this x1, x2 plane.